Hello and welcome to yet another video of Cornerstones of Math. Today we are going to draw a graph of the function y equals x cubed minus x divided by 2x squared minus 3. And I will draw it as precisely as possible without any help from the graphing calculator, but using the knowledge of mighty calculus. And I will introduce the entire process step by step, which you can apply to draw graphs of many different types of functions. First, before differentiating the function, we must properly understand the domain of the given function. The function right here is not particularly a weird one, but we still know that the value of the function does not exist when the denominator is 0. And the denominator is 0 when 2x squared minus 3 equals 0, so x squared equals 3 over 2. So x equals plus minus square root of 3 over 2, which can be written as plus minus square root of 6 divided by 2. So the graph doesn't exist at x equals plus minus square root of 6 over 2. Or you can say that the domain is the set of real numbers minus these two values. Next, it is useful if we can find any symmetry from the given function. Is the graph symmetric with respect to x-axis or y-axis or the origin? In order to find out, let's call this function fx and substitute minus x in place of x. Then, which can be written as minus x cubed minus x divided by 2x squared minus 3, which is minus the original function fx. This means that the graph is symmetric with respect to the origin. In other words, it is an odd function. Next, if there exist any intersection points with the axis, we can use them to our advantage when drawing the graph. First, what is the y-intercept? If x equals 0, then y equals 0. So the graph simply meets the y-axis at 0, 0, the origin. Next, the x-intercept. If y equals 0, then x cubed minus x must be 0. So x times x squared minus 1 must be 0. So x plus 1, x minus 1 must be 0. Therefore, x equals 0 and plus minus 1. Here, x equals 0 means the origin, and additionally, we have minus 1, 0 and 1, 0. So in conclusion, we know that the graph passes minus 1, 0, 0, 0, and 1, 0. And finally, here comes the fun part. We have to determine where does the function increase and decrease, of course by using the derivative. This will allow us to find its local maximum points and local minimum points. But here, let us do this with the next step simultaneously, which is determining whether the graph is convex or concave, that is, blown up or blown down, and we need a second derivative to do that. And of course, the inflection point, where the sign of the curvature changes. So first, the derivative. Using the quotient rule, we have derivative of the numerator, so 3x squared minus 1 times the whole denominator, 2x squared minus 3, minus the whole numerator, x cubed minus x, then the derivative of the denominator, 4x, divided by denominator squared, 2x squared minus 3 squared. And if you expand and simplify the numerator, you will obtain 2x to the power of 4 minus 7x squared plus 3, so this divided by 2x squared minus 3 squared. And the numerator is factorable, which gives 2x squared minus 1 times x squared minus 3. As you can see, the denominator cannot be negative, so the sign of the derivative is entirely dependent on the sign of the numerator. And the derivative becomes 0 when 2x squared minus 1 equals 0, or x squared minus 3 equals 0, which gives x value of plus minus square root of 2 over 2 and plus minus square root of 3. Like I said, the sign of the derivative follows the sign of the quartic function 2x squared minus 1 times x squared minus 3, which we can easily draw using these values. So the sign is positive, negative, and positive. For the derivative of the rational function given in the problem, the signs are the same, except the derivative is undefined when the denominator becomes 0, of course. And now the second derivative. Let's use this expression of the derivative because it is the simplest form to apply the quotient rule. Using the quotient rule again, the derivative of the numerator, so 4x cubed minus 14x, then the whole denominator, 2x squared minus 3 squared, minus the whole numerator, 2x to the power of 4 minus 7x squared plus 3, and the derivative of the denominator, so the power 2 comes to the front, and 2x squared minus 3, and by the chain rule, we have to multiply the derivative of this 2x squared minus 3, so we must multiply 4x divided by the denominator squared, 2x squared minus 3, now to the power of 4. Here we can cancel out 2x squared minus 3, so we have 8x cubed minus 14x times 2x squared minus 3 minus 8x times 2x to the power of 4 minus 7x squared plus 3 divided by 2x squared minus 3 cubed. And if you expand the entire numerator, from this part you will obtain 16x to the power of 5 minus 52x cubed plus 42x. And from this part you will obtain minus 16x to the power of 5 plus 56x cubed minus 24x, and 16x to the power of 5 cancel out. So we have first the cubic terms. We have minus 52 plus 56, so 4x cubed, and we don't have any square term, and the x term, 42x minus 24x, so 18x, which gives 2x times x squared plus 9 divided by 2x squared minus 3 cubed. Here, notice that x squared plus 9 is positive, so the sign of the second derivative depends on the sign of this x and this 2x squared minus 3 cubed. And you can easily identify the sign to obtain this result. Negative, positive, negative, positive. And at x equals 0, the second derivative becomes 0. So now that the signs of the first derivative and the second derivative are investigated, we can finally fill out the bottom row of this table, with the increase-decrease of the function is indicated with proper curvature. First, at the far end of the negative x region, where x is less than minus square root of 3, the first derivative is positive, so the graph increases, but the second derivative is negative, so the graph is concave. Therefore, the graph increases in this manner. Next, when x is greater than minus square root of 3 but less than minus square root of 6 over 2, the first derivative changes sign and becomes negative, while the second derivative keeps remaining negative. Therefore, the graph now decreases and also is concave, so the graph looks like this. Next, when x is in between minus square root of 6 over 2 and minus square root of 2 over 2. Here, the first derivative is negative, so the function decreases, and the second derivative is positive, so the function is convex. Therefore, now the function decreases in this manner, in contrast to the previous region. Then, between minus square root of 2 over 2 and 0, the first derivative positive, and the second derivative is also positive, so the graph increases while remaining convex. And for the rest of the domain, we can do it in a similar manner. So here the graph increases while being concave. Then in here the graph decreases while being concave. and here the graph decreases while being convex. And finally, for the remaining part, the graph increases while being convex. And at these boundary points, we can easily calculate the values of the function, which are minus 2 square root of 3 over 3, minus square root of 2 over 8, 0, plus square root of 2 over 8, and plus 2 square root of 3 over 3. So in the end, we can notice that the local maxima and minima occur here. So the local maximum points are minus square root of 3, minus 2 square root of 3 divided by 3, and square root of 2 over 2, square root of 2 over 8. And the local minimum points are minus square root of 2 over 2, minus square root of 2 over 8, and square root of 3, 2 square root of 3 over 3. And we can also notice that point 0, 0 is an inflection point, since the sign of the second derivative changes at the vicinity of x equals 0. So we have finished investigating derivatives, but there remains one more thing to do. Checking for asymptotes. The hint for possible asymptotes can be obtained from the expression of the function itself. First, from the condition that makes denominator 0, we can immediately find the vertical asymptotes. Note that the denominator becomes 0 when x equals plus minus square root of 6 over 2. This means that whenever x approaches either of these two values, the value of y goes to either positive infinity or negative infinity, depending on the approaching direction. This means that we have two vertical asymptotes, x equals square root of 6 over 2 and x equals minus square root of 6 over 2. But we are not done with the asymptotes. You see, we have a rational function where the degree of the numerator is 3 and the degree of the denominator is 2, so its net degree is 3 minus 2, which is 1. So it's sort of same degree as the linear function. Therefore, it seems that our function can have an asymptote that is a linear function, but not necessarily vertical or horizontal one. And I will show you that is exactly the case here. However, this original expression where the numerator has higher degree is rather inconvenient, so let us sort of divide the numerator with the denominator to split this fraction. For this function, we can do that by simply splitting the numerator into x times 2x squared minus 3, the denominator. Then we have 2x cubed terms, so we have 1/2 at the front, and the remaining term, which is 1/2 x, which is essentially the remainder of the division. Then we have 1 over 2x plus x divided by 2 times 2x squared minus 3. Now for this part, the denominator has the higher degree. So as x approaches positive or negative infinity, this part goes to 0. So we have a linear function part plus the part that approaches 0, meaning that our function approaches 1 over 2x as the magnitude of x becomes very large. Or in a more formal manner, we can say that the limit of y minus 1 over 2x is 0 when x approaches positive infinity or negative infinity. This means that the line y equals 1 over 2x is also an asymptote. To summarize, asymptotes are two vertical lines, x equals plus minus square root of 6 over 2, and one oblique line, y equals 1 over 2x. So now we can finally draw the graph. We are definitely going to use this table. Also, let me state additional information we have obtained right here, because it will be helpful to us. Here, let us indicate these asymptotes first. So we have these three asymptotes. Now we draw the curve according to the table. So for this part, the graph increases then decreases, but the curvature remains concave. So we have the graph, and of course the graph has to approach these two asymptotes. And this is the local maximum point, minus square root of 3, minus 2 square root of 3 over 3. Now let's move on to the next part. Here the graph falls down from the positive infinity, so that the vertical line is an asymptote. then hits the local minimum point, then starts to increase all the way up to origin. And as you can see, the graph is convex in this region. This local minimum point is minus square root of 2 over 2, minus square root of 2 over 8. And it's essentially the same process. So the graph increases, then decreases all the way down to negative infinity. And as you can see, the graph is concave now, because that's what we've obtained from the second derivative. And this is the local maximum point, square root of 2 over 2, square root of 2 over 8. And finally, we have this graph, again approaching the asymptote y equals 1 over 2x as x goes to infinity. And this is the local minimum point, square root of 3, 2 square root of 3 over 3. Of course, you can also use the fact that the graph is symmetric with respect to the origin. So you can just investigate the graph on either positive or negative x and rotate the graph around the origin to obtain the other half. Also, speaking of the origin, you can see that as graph passes the origin, the curvature changes from convex to concave. That is, this origin is the inflection point. So this is the entire graph. And if we compare this with the graph drawn by Desmos graphing calculator, as you can see, my drawing is pretty darn close to the actual precise curve. So that was the method of sketching a graph of the function using our combined knowledge of limits and calculus. If you enjoyed this video, please hit that like and subscribe buttons and go check my other contents as well, and I will see you in another video.